All right, so today we're going to finish talking about end behavior. Let's go ahead and do that. We were talking about limits, and so far we've focused on finding limits as x approaches plus or minus some real number c. The next thing we're going to do to finish out this section is to talk about limits as x approaches plus or minus infinity. So instead of thinking about like, okay, let's approach, this finite value, we're going to basically be looking at what happens if I send x off to this infinitely large value or send it off in the other direction towards negative infinity. So to start this out, you learned in college algebra or whatever your algebra class was about end behavior. So you did this when you were graphing polynomial functions, and so that you had some sort of a sense of what the shape of your graph would look like. In order to do that, you were able to determine based on the function what sort of end behavior it had. Now, when you were doing this for polynomials, you knew that even graphs either went both up or both down, both down, or you knew that odd graphs could have one leg that went up and one down, or they could go in the reverse. And you determined that based on the degree of the polynomial and the sign of the polynomial. Right now, we're mostly just going to be functioning on actually evaluating these using limits and what we know even about asymptotes. So back to what you learned about in algebra, if you look at a graph like this, the end behavior is just talking about what are the values of y doing as x gets infinitely large or infinitely small. So think about what happens as x is approaching infinity. Now, of course, we have arrows on this graph to indicate that it's just going to continue on in this direction. So we can't expect that all of a sudden it's going to like zoom back up here. It's not going to happen. The arrows are just indicating that this behavior is going to continue. So as x gets increasingly large, heading off towards infinity, we're talking about these values of x. Well, as the graph moves to the right, the values of y are going to continue to decrease. So as x goes to infinity, f of x or y goes to negative infinity. And we could say something similar as we look at the other end of this graph. So as x becomes smaller, as I move to the left, the y values go up. So as x approaches negative infinity, f of x or y will approach infinity. They're just going to continue to go up without bound. Now, something like this next example has similar behavior in some respects, but now we're dealing with a situation where we have a bunch of asymptotes. I want to point something out right now. A lot of times students will say, how can this be an asymptote, a horizontal asymptote? The graph crosses through it. How can that be? When you think about horizontal asymptotes, you can't think about them the same way that you think about vertical asymptotes. A vertical asymptote really is a situation where you cannot cross that line. It's a boundary. You can't touch it. You can't cross over it. Horizontal asymptotes don't work in quite the same way. The vertical asymptote works the way it does because we have this function and we can't have undefined function values. The horizontal asymptote is only just serving to guide the end behavior of the function. Sometimes you might have something going on in the middle of the function where the graph is going to end up crossing through a horizontal asymptote. That happens and it's fine. There's nothing wrong with that because the middle of the function has nothing to do with its end behavior. What we're mostly focusing on for horizontal asymptotes is what's happening to the end behavior of the graph. So as x gets really small or really large, what's happening to the y values? And those y values are going to be bounded by those horizontal asymptotes. So even though we can, in this situation, we can cross through that horizontal asymptote in the middle, we can't cross through it at the ends. So that the asymptote is guiding the end behavior of the function as x gets increasingly large or increasingly small. So does that make sense? I just want to make sure that's clear because students are always just like, this doesn't look right to me. I know it's okay with the horizontal asymptote to cross it somewhere in the middle of the function. All right, but same idea here with the asymptotes. In this case, as we look at values of x that are getting increasingly large, now we've got this situation with the horizontal asymptote, whereas x gets really large and moves off to the right, the values of y are actually decreasing down until they start to reach this value at y equals 2. Now, they can never actually touch this value at y equals 2, but they're going to approach it for the rest of time, forever and ever and ever. As x gets increasingly large, f of x will just get as close to 2 as it possibly can. It's going to be at 2.01, 2.001, 2.0000, and it's going to get so close, but it's never going to touch. Same idea over here on the left. As x gets increasingly small, as I move over my values towards the left, the values of y are going to approach 2, but this time they're going to approach from below 2. So they're going to be approaching values like 1.9, 1.99, 1.999, 1.999, and they're going to get super close, but they're never going to quite touch y equals 2. So we've got a couple different things that we could have happening as x approaches in positive or negative infinity. You could see that the graph values for y also approach positive or negative infinity, or you could have this situation with the horizontal asymptote controlling that behavior. So let's look at some examples of this. We will first evaluate the limits for these example graphs. The first one is asking you about the limit as x approaches infinity of your graph f of x. So as x gets increasingly large, we're just looking at values as x moves to the right. We're looking at values of y. So I'm looking at values as x gets increasingly large heading to the right. And you can see that as x gets larger, the values of y, which originally started down here, are going to start to go up, 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 up. They increase. They're going to head up towards this asymptote, which I know is a little bit hard to see, but it is actually at 3. This tick mark right here would be 2. I know it's not labeled because otherwise the label would overlap and you wouldn't be able to see it anyway. So that would be 2. So we're in between 2 and 4 here. So that puts the horizontal asymptote at 3. So we would say in this case that the limit, the value that y approaches as x approaches infinity, is 3. So that's the way that we're going to think about horizontal asymptotes in terms of limits. So mostly when we talk about limits at infinity, we're really talking about horizontal asymptotes. But we now have this fancy new notation that we're going to use to talk about them. We're going to do the same thing now, but looking at values of x as x moves over to the left. So I'm looking at these values on the graph. Notice that as I'm moving over towards the left, I'm actually looking at this other branch of the graph that starts up here and heads down from the vertical asymptote, and it's heading down towards the horizontal asymptote at y equals 3. So same idea here. We've got this horizontal asymptote that's controlling the end behavior of the function. So we would say the limit of f of x as x approaches negative infinity. Those would be the values that y is approaching. Well, they're approaching 3. So both of those limits, whether x is going to positive or negative infinity, will be 3. For number 2, we're going to do the same thing. We're going to look at the limit as x approaches infinity and as x approaches negative infinity. So for A, we're focusing on what's happening to y as x gets increasingly large. So in this case, you have a vertical asymptote here at y equals negative or x equals -4. And then you have something called a slant asymptote, which you should have seen in your college algebra class. A slant asymptote, we're going to see here and there in this class. We might not use them very much. You might see them again in curve sketching, but it's going to control the behavior of your function very similar to the way that a horizontal asymptote would, except it's slanted. So as you're looking at these function values, as x gets increasingly large, I'm looking at this branch of the graph here that's in red. And as x is getting larger, notice the y values are decreasing. So as x is moving to the right, the y values are going down. And you can see that this is just going to keep happening and it's going to continue on its entire domain. So because this behavior is not going to change, we can state that the limit or the values that y will approach is negative infinity, because these y values just keep going down forever and ever and ever. They have to. They're controlled by that slant asymptote. Looking at this as x moves to the left, as x moves towards negative infinity, now I'm looking at this other branch of the graph down here below the slant asymptote and to the left of the vertical asymptote. So as x is getting increasingly small, moving off to the left, the values of y will increase up to the slant asymptote. And they're just going to keep going up and up and up and up. So it's not like a horizontal asymptote where they're going to level out. They're just going to keep increasing forever. So in this case, we would say that the limit as x approaches negative infinity, in this case, is positive infinity. Okay. Evaluate the limit numerically by completing the table. I'm really glad we're doing this because we always need more work with evaluating limits numerically. It's such an important skill, and I feel like students only do it when you tell them to do it, but it's just so useful for evaluating a limit, especially if you're not sure what to do, just pop in some values. So our function is going to be 1 over x squared. We're looking at what's happening to these values of x. I'm going to put this into my calculator real quick here. 1 over x squared is the function. Oh my goodness. Put myself into function mode. You should already be in function mode. Sorry, I clearly picked up the wrong calculator. 1 over x squared. And then I'm going to enter these values in my table. I'm using a different calculator, so I want to make sure that if I go into table set, that my independent variable is set to ask. So it is, I'm good to go. It doesn't matter what your table start is because you're setting it to ask anyway. If you had this set to auto, it would just start the values for you at -0.5. And then in my case, it would increase them by 0.1. I clearly had this set for something specific that I was doing. But I'm going to set this to ask. Now you might be wondering, like, why does she already have values in there? It's because I was already using this. So I can just go over them and enter new values. If x equals 10, y equals 0.01. If x equals 100, then I know that now I'm looking at 1 times 10 to the -4th. We're going to talk about that scientific notation here in a second. For 1,000, I have 1 times 10 to the -6th. Now, in the last lesson, or in the previous part of this, we got answers like 1 times 10 to the +4th, and we were talking about how those were these huge numbers. But remember, when we are using scientific notation and the exponents are negative, we're actually moving in the other direction for the decimal. So when this says 1 times 10 to the -4th, you're taking 1, you're assuming the decimal's right after the 1, and then you're moving it to the left 4 places. So 1, 2, 3, 4. And that's where the new decimal is going. That means you have 1, 2, 3 zeros that are going in front of the number. So if you want to put that in the box as well, 0.0001, that might be helpful to you. And we'll do something similar for the 6, but you can tell that for the -6 that we're just including 2 more zeros before the negative. So we would say this was 0, 0, 0. And then we'd be moving to the left 2 more decimal places, 0, 0, 1. Now, these values are still positive. It's only the exponents that are negative. So that's just telling us that we're moving to the left instead of to the right. So notice that as x gets increasingly large, so we're going from 10 to 100 to 1,000, as x is getting larger, y is actually getting smaller. Now we have to determine, like, exactly where does it appear to be going. Well, imagine that if I kept making x get larger and larger and larger, y would keep getting smaller and smaller and smaller. And eventually y would have, if it could go on forever, at the end of time, it would reach 0. But it cannot go on forever because time will never end. So we're going to go ahead and just say that the limit, the values that y approaches, is 0. And we can look at this a few different ways. Remember, we had talked about, let's see, well, let's look at this in the graph. I already have this function. So now when I graph it in my graphing calculator, just by hitting the graph button, this is what it looks like. So as we send x off to positive infinity, we're looking at values that head off to the right. We're seeing that our y values approach 0. Another way, I'll just jot this down so it's on the notes. Looks like that. So that means that y is heading off towards y equals 0. Another way that we would see this is if you try to evaluate this limit algebraically using direct substitution, you would end up getting 1 over infinity squared. Well, infinity squared is still just infinity. I know that seems odd, but you can't have more than infinity. So if you square it, it's still just infinity. My kids don't believe me on this. They're like, no, infinity plus infinity is more than infinity. And I understand the logic, but it's infinity. It doesn't really work like that. The idea here, though, is if you take a real number and you divide it by a value that's infinitely large, the quotient is going to become infinitely small and will head off to 0. So you can use this logic anytime you're evaluating these limits, assuming that you're actually going to get a value here. But if you're just taking a real number and dividing by infinity, the quotient will always be 0. It's just a rule. And it makes sense. All right, last thing we're going to do here is we're going to evaluate some limits of rational functions. So remember that rational functions are functions that can be written as one polynomial over another polynomial. When you think rational, you should be thinking ratio. And when we think about a ratio, we think about a fraction. So this is these are functions that are written as a fraction of 2 polynomials. Okay, so we're going to do this algebraically. And there are 2 methods. Officially, there are 2 methods. I have another method, though, that I'm going to show you. And I personally think it's the best method. Sometimes students are like, no, just show me one method. And I get that. If you'd like, you can only use the best method, which I'll tell you what it is in a second. But I do want you to see the other 2 methods because I don't want you to feel like, oh, I have never seen this before if you go on to your next math class. So I'm going to show you all the ways just so that you've seen them and they'll somehow at least be hopefully little tidbits in your mind for later. Method 1, divide the numerator and denominator through by the highest power of x in the denominator. The highest power of x in the denominator. And then, we should say simplify. Sorry, I should give you more space for that. Simplify, and then use the fact that the limit as x approaches plus or minus infinity of c, which is some real number, divided by x to the nth power is 0. Now, we kind of just did this in the last thing we did on the last page. We talked about the fact that if you take a real number and you divide it by infinity to a power, you're going to get the quotient to come out to be 0, or negative infinity to a power. It's just a real number divided by something incredibly large. And whether it's positive or negative infinity, you're just going to be approaching it from a different direction. Where c is any real number, and n is a positive real number. Note, the answer you get should coincide with what you should recall about horizontal asymptotes of rational functions, which is what leads us into talking about method 2. Now, this is kind of like the new method for doing things, method 1. Method 1 is like the calculus method. If you were to take either this class or Calc 1 or Calc 2, you would use this fact a lot. Although method 2 is another fact that you would use in both classes. It's something that comes directly from algebra. So these are rules for horizontal asymptotes. And again, this is for f of x is n of x over d of x, the numerator divided by the denominator. So back in algebra, you learned some rules for horizontal asymptotes. You probably don't remember what they are. I'm going to remind you now. There were 3 different things that could happen. So the first thing is if the degree of the numerator, we'll call it n of x, since we have it written like that, is greater than the degree of your denominator, d of x, then y approaches plus or minus infinity and you have no horizontal asymptote. So that could happen. So that would be if the degree, oh, maybe you don't remember what the degree is. Well, I should remind you of that. The degree of a polynomial is just the highest exponent you see on any given term. So if it's a quadratic, you have, ax squared plus bx plus c, that's of degree 2. If it's cubic, it'll be, ax cubed plus bx squared plus cx plus d. You're just taking the highest exponent that you see. And of course, we're going to go through some examples of this too, but it's just your highest exponent. Well, these are for rational functions. All right, the second thing that could happen is that the degree of the numerator could be less than the degree of the denominator. So if the degree of n of x is less than the degree of d of x, well, if that's the case, then your horizontal asymptote is y equals 0. So this would be sort of like what we saw with that last example. I know it's so close. Let me find it. The degree of the numerator is less than the degree of the denominator. Well, when we did this problem, the degree of the numerator is actually 0 because it's just 1x to the 0. And then the degree of the denominator would be 2. So it'd be x squared. So it'd be a second degree polynomial. The degree of the numerator is less than the degree of the denominator. And we did indeed get that this limit was 0. The horizontal asymptote is 0. So remember, those are synonymous. Okay, the last one tends to stick with students a little bit more. They tend to forget which one of these is which, but the last one is a special case where the degrees are equal. So if the degree of n of x is equal to the degree of the denominator, d of x, then your horizontal asymptote is the ratio of the lead coefficients. So remember, it's always in the form of y equals, which is a horizontal line. The ratio of the lead coefficients. Coefficients, remember, are the numbers that are being multiplied by the variables in your polynomials. And the limit of f of x in all of these cases, the limit as x approaches plus or minus infinity of f of x is the horizontal asymptote. It's the main thing that we need to be taking away from this. So I'm going to be going over a couple of examples of this, and I want to show you how to do this using both methods. And then as we go through method 2, I'm going to show you a way to sort of always use this third option by setting their degrees to be equal, because like I said, a lot of times students will remember the third one, but they won't remember the first two. They're like, which one's which? One of them was like no horizontal asymptote, and one of them was horizontal asymptote equals 0. And then they're just guessing. So I'm going to show you a way that we can use these and then also just focus on that last one. So that's kind of my goal. All right, so I'm going to fit 2 examples on this page just so you have an idea of what sort of spacing situation we're dealing with. Example 1. So this will be the limit as x approaches negative infinity of 4 minus x squared divided by 2x squared plus 5. Oh, by the way, I'm going to put these two examples here, but if you find that like, I don't have enough space, I had your notes made single-sided. So you can always feel free to just look at the left side of, if you put these in a binder, just, write some off to the left so that you can sort of see it right next to there on the page. That's the whole reason I did that, is just so that you could expand out. I know some students write even smaller than I do, and other students need like twice the space. Okay, so here's our rational function. It's 4 minus x squared over 2x squared plus 5. And this time we're sending x off to negative infinity. Method 1 stated that we should divide the numerator and denominator through by the highest power of x in the denominator, simplify, and then use this fact. So I'm going to show you how to do that. You might find this especially useful also because if you were to go on and take regular old Calc 1, you're not going to only be dealing with rational functions, but you'll also have some radical functions, and you'll have to use method 1 or that type of reasoning for rational functions because they don't, or for radical functions because they don't have these horizontal asymptote rules. These apply to rational functions. So this method works more generally, whereas method 2 is basically when you have rational functions. All right, so method 1, we're going to multiply through by the highest power of x that we see in the denominator. So as I'm looking at the denominator, the highest power I see of x is x squared. So the whole fraction, every single term, is going to get divided by x squared. Now, whether you divide by x squared or 2x squared does not matter to me. I'm just going to divide by x squared. So I'm going to take the 4 in the numerator and divide it by x squared. The x squared in the numerator gets divided by x squared. I know I didn't actually put the limit back on, but maybe I will just because I want you to get used to using good notation. And then in the denominator, we'll have 2x squared divided by x squared plus 5 over x squared. Now we're going to simplify. So you'll notice that in the numerator, you have an x squared over an x squared. Remember, that's not 0, it's 1. Don't forget to write the 1. It will make a difference sometimes. All right, and then in the denominator, we'll have 2 plus 5 over x squared. So now we've simplified it, we've divided it out, and you might be wondering, like, why would I want this versus that? Well, for method 1, we have to have forms that have constants in the numerator and variables in the denominator. Because remember that if we take a constant and we divide it by a number that's getting increasingly larger, increasingly small, that quotient is going to head off to 0. So that's the fact that we're using here for method 1. The constant divided by x to the nth power, when you take the limit as x goes to plus or minus infinity, will be 0. What that means then is that when we're taking this limit, and we're going to sort of apply this term by term, the limit of 4 over x squared is going to go off to 0. Remember that the limit of a constant is just a constant. If we were to just think about this using direct substitution here, and then we'll have 2 plus, and then if we send this one off to infinity, that quotient will also go to 0, or I'm sorry, negative infinity. The quotient will go to 0. So we end up getting here a value for the limit of negative 1/2. So that's method 1. Now I will show you method 2. Method 2. I'm going to examine this expression first. Note that for method 2, we're looking at the degrees. because I'm trying to figure out which rule this fits for the horizontal asymptotes. But if you're staring at this and you're like, oh, well, 4 has a degree of 0 and x squared has a degree of 2, clearly this follows rule number 2. That's actually not true, because you don't have this in descending order currently. The highest power that you have on x in the numerator is 2. And in the denominator, it's also 2. So your degrees are actually the same, which puts you into case 3 here. If you're not sure about that, just rewrite it. So I would say that this is the limit as x approaches negative infinity of negative x squared plus 4 divided by 2x squared plus 5. So the way that this rule is going to work is, as long as the degrees in the numerator and denominator are the same, then the limit is going to be y equals the ratio of the lead coefficients. Well, I mean, we don't really need the y when we talk about the limit, but you can just take -1, which is the coefficient on the lead term in the numerator, and divide it by 2, which is the coefficient of the lead term in the denominator. Done. Same answer, 2 different ways. Now, I did say, remember, that I was going to show you a method 3 that's kind of using these rules. But in this case, we don't need that because method 2 already used that third rule. So I'm going to expound on that in the next example, because I do have one more for you here before we finish this off. Last one is example 2. The limit as x approaches positive infinity of 4x cubed minus 2 divided by 5x to the 5th minus 3x cubed plus 1. So for method 1, remember that we're going to be dividing every term by the highest power of x that you see in the denominator. So I'm going to rewrite my limit. And then I'm going to take each term and I'm going to divide it by x to the 5th power, because x to the 5th is the highest power of x that I see in the denominator. So I'm going to take 4x cubed and I'm going to divide it by x to the 5th. 2 will also be divided by x to the 5th. Remember, the goal here is to get forms of c over x to the nth power. We have 5x to the 5th over x to the 5th minus 3x cubed over x to the 5th plus 1 over x to the 5th. And as long as I divide every single term by the same quantity, then I'm not actually changing anything. So now we'll simplify. This becomes the limit as x approaches infinity of 4 over x squared minus 2 over x to the 5th divided by 5 minus 3 over x squared plus 1 over x to the 5th. And now you can use this rule again repeatedly when we have a constant in the numerator and x to the nth in the denominator. Assuming x is heading to plus or minus infinity, we can get those terms to zero out. So our limit here, oh, I'm running out of space on this one. I'll just pop it down here. As soon as I start to plug in values for x or to evaluate the limit, I'm going to drop the limit notation, kind of like how I did that up here. 4 over x squared, that will go to 0, minus, and then 2 over x to the 5th will go to 0. And in the denominator, we have 5. There's nothing to evaluate there. Minus 0 plus 0. And 0 divided by 5 is 0. So that's how we would do this with method 1. And by the way, you can always check these. I didn't say it was method 1. I should do that. You can always check these in your calculator to make sure that you get this to match up and verify that as x approaches infinity, y approaches 0. I think we'll do that when we wrap this up here at the end. Method 2 would be to look at the degrees in the numerator and denominator. And in this case, you would note that the degree in the numerator is less than the degree in the denominator. 3 is less than 5. And then you'd have to remember, like, oh, I don't know, which case is that? And then you'd go back and say, all right, the degree in the numerator less than the degree in the denominator, horizontal asymptote is y equals 0. And thus the limit is also y equals 0. Okay, so you have two different ways of doing the same thing. So the way that I like to do this, because like I said, a lot of times I don't remember which one's which either. I'm like, I don't know, the degree in the numerator, degree in the denominator. If they're not the same, I can't remember the rule. So when I was in grad school at NIU, I was a TA for a while, and there was a fellow TA that I worked with, and she taught me this, and I will never forget it because I use it all the time. And I don't even know, she learned it, I think, from the teacher she was working with, student teaching. Maybe you've seen this before. What we can do, though, is we can turn every single method 2 problem into a case where the degrees are the same. So I could rewrite, I'm going to say another method. Rewrite so that n of x equals d of x. And if you're kind of like, how would I do that? Well, I'm going to show you. It's actually really straightforward. Let's say I wanted to rewrite this expression. I've got it right here, my limit. I can say that this is the limit as x approaches infinity. And I can force these two to have the same degree if I just put a 0 coefficient on the term when I place it, in this case, into the numerator. So if I want these to have the same exact degree, I can make the numerator here 0, x to the 5th, and then I can add on the 4x cubed and the minus 2. And then the denominator will stay the same. And as long as you have the same degrees in the numerator and denominator, you can apply this ratio of lead coefficients deal. So we would say that the horizontal asymptote is like y equals the ratio of the lead coefficients. So that means y equals 0 divided by 5, which is 0. And you get the same answer. So you can always do that. And it doesn't have to be the case that you have to put the 0 in the numerator. Let's say you had a situation where these were reversed. You could still put that 0 in the denominator. And then if you had to take 5 and divide it by 0, you'd be like, wait, 5 divided by 0 does not exist. I can't divide by 0. Well, in that case, you don't have a horizontal asymptote, because now you're again in that case of the numerator's degree being greater than the denominator's degree. Okay, so it'll work either way, whether you have to add it in the numerator or denominator. Okay, but that's all I have to say right now about limits, and we'll talk more about limits in the next section when we talk about one-sided limits and continuity. So I'm sure that you will be anxiously awaiting that. All right, let me know if you have questions. Have a wonderful rest of your day.